Welcome to the section on corrective measures. The first part of the section will be on data augmentation, and then the next will be an exploration on the modifications which were made on YOLO version 1 and YOLO version 2 to obtain YOLO version 3. Now, data augmentation, as we know, comes to solve the problem of overfitting. And it's important to know that overfitting can be very dangerous, as it can mislead us to thinking that a model is best fit for testing in a certain environment. So supposing that we have images like this where the persons are quite small with respect to the image width and the image height, and then after training on this kind of image, you now are presented an image where the person occupies practically almost all the image, you will find that the model will struggle to see that new image you presented is actually that of or contains a person. So it's very important to get data that's representative of the test set, and then also important to make sure you get as much data as possible. Then apart from this, we could augment already existing data like this one. So supposing we have this data, we could create another image. So if you have this image, we could create another image which is made just by doing a left-right flip on this other image right here. So as you could see, this image has been flipped so that we obtain this. Now another way we could augment this data is by increasing the saturation of this image. So as you could see, now we have created this new image with a different saturation. Now it's important to know that there are so many other ways we could do data augmentation, and when carrying out a project, it's very important to make use of this technique as much as possible. Now secondly, we shall classify this data augmentation techniques into two main groups. Now this first group that you see right here involves data augmentation where the modification which is done on the input image doesn't actually modify the output labels. So this image, if we have a box surrounding this, that box is going to be on the same position. If we have this box surrounding this person, it's the same box surrounding this person. Now we also have the second category where if a box was found here, the box now changes position. So it means the output labels have to be modified. Like for example, this here, you see it leads from this to this new position now, whereas with this there wasn't any change in position. So we have these two categories which are differentiated by the fact that some may change the output labeling while others don't. We can show this clearly from this example where we have this image, we plot out the image, and this is what we get. Then we take this image and then modify it using TensorFlow.image.adjust saturation. So using this adjust saturation, we actually specify the saturation and then plot this out again. We see how the image just saturation has been modified. Now another transformation we could do is a flip left right. So we could take this off, flip left right. Now all these different transformations we could do are actually found in the documentation of TensorFlow. So you could get to documentation to see all the different transformations you could do so that you don't have to redo them on your own. So let's run this. We have this error because all this is on. We don't need that. Run that again. And there we go. So we see how we flip this image left right. So now instead of this, we now get this image, but with the difference that the bounding box positions actually change. So we have to take that into consideration. Now to take that into consideration, we could get into this data generation function we had defined previously, where we had an image, we actually take in the x values, then with this we get the bounding boxes, and then go and get the y's. So like for example, this we get the generate output function to give us the actual output we shall use in training our model. Now once we have this, we could for every image generate another input into our data set. So this means that if we have a batch size of say for example 32, then for every batch size we shall now have an increase of 32 other inputs or images to work with. So our batch size now has been multiplied by 2. So here we have this multiplied by 2. Then we get to this point. For this, instead of having I, we have 2 times I, and we could have this such that when I is equals 0, for example, we have x0. When I equals 0, still we have x of 0 plus 1, so we have x1. So x0 will be for the actual data, and then x1 will be for the augmented data. When I will be 1, we'll go to x2. So that's how we go from x0, x1, x2, x3, x4, x5, and so on and so forth. So with this, we have the actual data, we have the augmented data, which is basically gotten from the flip left right function, which comes with TensorFlow.image module. Now we have our image to array, then we have the image right here, which we got already. The next step, we had the bounding boxes, which we gotten from the XMLs. Then we generated outputs to give us yi. Again, here similarly we have this. So we have this times I, and then we have y of 2i plus 1, such that we have the evens coming from the real or from the actual data, and then the odds from the augmented data. So there we go. And then we now have this new bounding boxes. So let's now define a way in which we could work with these bounding boxes. Let's uncomment this part. Then there we go. So we have this new bounding boxes right here, and we need to actually get their values with respect to the previous bounding boxes. Coming back to the slides, let's look at the way we could do this. Supposing we want to get this distance from here to this point where we start looking at touching the bounding box on which surrounds this big aeroplane right here. Now we may have calculated the distance to be 102. So from here to here is 102. It means the x mean for the bounding box surrounding this is 102. But in the process XML function, what we did was we divided the x mean, y mean, x max, y max values by the width and the height. And that's just what we've done here. Now dividing like this just tells us that this from this distance from here to here is like 20% of the whole image. So if we want to swap this, instead of doing just instead of having this, like supposing we did not divide this, or supposing we had this input 102, after doing the swap, normally this position should be at position 500 minus 102, as you could see here, because obviously the distance from here to here will still remain 102. So from this to this, as you could see here, from this to this should be 500 minus 102. So that gives us 398. Now the next point is 398 occupies what fraction of the image? That fraction happens to be 0.796 of the image. But another easy way to look at this is simply to say that after dividing by 500, as you could see right here, we have 0.2. Then we simply have 1 minus that 0.2, which gives us now 0.796 again. So that's how we obtain the new positions for the x mean, x max, y max. But also note that this transformation is done only on the x-axis, so the y mean and y max remain intact, while the x mean and x max have been modified. So that said, that's how we obtain this, where we have for each being the bounding boxes, because we may have different bounding boxes. For each bounding box, we have 1 minus x mean, we maintain the y mean, 1 minus x max, we maintain the y max, and then we have the class. So basically that's what we have, and then we have this new bounding box. So that's how we output this, and that's how we do data augmentation when the outputs have to be modified. Now also note that we may have a situation where we want to do this data augmentation for different transformations, which is advised actually. So in this case, we had, say, we just had I, or let's say number of augmentations. Let's call it num augment plus 1, because the 1 is actually the image, the actual image we're working with. For this, we had just one num augment, so we have that, and then we replace right here. So that's it. Now we do the same again for all this. We have this, we could take this off. Let's copy this here, and then copy right here, and same down here. So that's it. So we have this such that if we want to do, let's say, 2 data augmentations, we just have to modify the num augment to 2. We have 2 here, we have 2 here, we have 2 here, we have 2 here, and 2 here, such that we'll be able to data augment our initial data twice. So we'll take this back, and then we can head towards training. So that's fine. Could run this, and after training, you have the results we get. Now also, when we're dealing with the category of data augments methods where the labeling or the outputs don't actually change, we should note that we could use this readily available data augmentation models, which are in this tf.keras.layers.experimental.processing right here. So here we have the random contrast, for example. With a random flip, you see that you need to actually modify the labeling, and we've taken an example where we could modify the labeling. For the random contrast, as you could see right here, we don't actually need to modify the labeling because we just adding some contrast into the image. So supposing we have this right here, which we could copy, we will now get into our code and then just add it up as a layer in our model. So right here, we could copy this. We've already imported this, so we could take this now. That's fine. We could take this off, and then we choose a factor, say 1.5. So that's it. So with this now, we are actually doing data augmentation, but we are able to do this simply because we ensure that the outputs aren't modified. And this goes the same for the rescaling process that we had done already. Apart from that, the tf.image also has many transformations which you could explore. As you could see right here, we have this random flip up down, random hue, random JPEG quality, random saturation. We have many other different transformations which we could use in our model. And also note that it's important sometimes to use a set of transformations, evaluate the way they affect the model quality, and then filter off or get the best transformations to be used for data augmentation for the model. Now, what does that mean? It means that supposing we want to work with adjust contrast, adjust gamma, and adjust hue transformations. Now, after testing with this, the model has, suppose that the model gives best performance for this, the model, it doesn't change much when we use this, or the model doesn't change much when we use this, then it simply means that in the final model we had to use to train our model for deployment or for testing, then we should obviously use this adjust contrast instead of trying to work with transformations which don't actually increase or better our models in any way.